This is Chapter 4, Atoms and Elements, and Section 5 is Isotopes and Atomic Mass. In the last video, we talked about atomic number and mass number, and we also briefly mentioned this concept of isotope a couple of times without really giving it a formal definition. So before we talk about what an isotope is, it helps to remember what an atomic number is, right? And what makes an atom the specific element that it is. So the atomic number is the number of protons in the nucleus of an atom. And that is what makes an atom a specific type of element. So for example, any atom in the universe that has one proton in its nucleus is hydrogen. Any atom that has two protons in its nucleus is helium. Down here we can see magnesium, and its atomic number is 12, and so any atom that has 12 protons in its nucleus must be magnesium. That is the definition of what it means to be magnesium, right? But we also have this mass number, right? For magnesium, in this case, it's 24. Hydrogen, sometimes the mass number is 1, but there's also hydrogen that has a mass number of 2. So what's the difference? Well, the difference is in the other subatomic particle in the nucleus. Right? The other subatomic particle in the nucleus, you may remember, is the neutron. And so isotopes are atoms that are the same element because they have the same atomic number, meaning the same number of protons, but they have different mass numbers because they have different numbers of neutrons. Okay? So the protons are the same, but the neutrons are different. Because the protons are the same, they're the same element, but because the neutrons are different, they have different masses, right? So what we're saying is, in this example for magnesium, not every atom of magnesium has exactly the same weight. Some of them have a mass number of 24, like you see here, but there are others that may have slightly more or slightly fewer neutrons. Okay? And so we can distinguish these isotopes by their atomic symbols. Here you see, again, the example for magnesium. You have the chemical symbol, Mg, for magnesium. And then I already pointed out the atomic number in the lower left. So for magnesium, that's always going to be 12. Sometimes that's omitted because it's redundant in a sense, but for completeness, we're showing it here. And then you also have the mass number in the upper left, right? And the mass number, remember from last time, is the number of protons plus the number of neutrons. So in this case, if you take the 24 mass number and you subtract out the 12 protons that magnesium has, you're going to find that this particular isotope of magnesium also has 12 neutrons. 12 plus 12 equals 24. To get used to this idea, to understand it a little better, it really helps to just jump into a couple of examples. So for these three isotopes, these three isotope symbols that we have here, the question is, determine the number of protons, neutrons, and electrons for each one. So for each of these symbols, given the atomic symbols of the specific isotopes, we want to be able to figure out how many of each of the three subatomic particles there are. And to do that, we're going to need a couple of things. We're going to need the atomic number, and we're going to need the mass number. Okay? So let's do that. Here's a blank table to help us organize that information. And so the question is asking for the number of protons, the number of electrons, and the number of neutrons. But before we can figure out any of those numbers, we have to understand that really what we need is the atomic number and the mass number. Okay? So where do we get the atomic number and the mass number from? Well, for an isotope symbol like we have here, it's very easy. The atomic number is this lower left number here. Okay? So for oxygen, the atomic number is 8. For phosphorus, the atomic number is 15. For zinc, the atomic number is 30. Okay? Now, if that number for some reason is missing, that's okay because the atomic number is always the same for a given element. So if we know that we're dealing with oxygen, we can just go to a periodic table, look up oxygen, and find that the atomic number is 8. And it's always going to be 8. If it's not 8, then it's not oxygen. Okay? The next column is asking for the mass number, okay? And the mass number is also given in the isotope symbol, and that's the other number, right? If the lower one is the atomic number, then the only number left must be the mass number. Another way to remember this is that the mass number includes the number of protons and the number of neutrons. So the mass number is always going to be greater than or equal to the atomic number. So the bigger number of the two is always the mass number. Okay? So here we have 16 is the mass number for this particular isotope of oxygen, 31 for this particular phosphorus, and 65 for this particular zinc. Now again, I say these particular ones because not every oxygen atom has a mass number of 16. So if you want to know the mass number, you have to be given a symbol like this, an isotope symbol like this, or told the information in some other way. So once we have those two pieces of information, then we can solve for the rest of the table, right? The next one is the easiest. The number of protons is just the same as the atomic number. So we just put the same information into that column. 8 protons in a nucleus of oxygen, 15 protons in a nucleus of phosphorus, and 30 in the nucleus of zinc. Okay? Then it's almost as easy to think about the number of electrons as long as we're assuming that these are neutral atoms and they don't have a charge. That means they're not missing any electrons and they don't have any additional electrons. So the number of protons must be exactly balanced by the number of electrons. Okay? So again, for a neutral atom, oxygen has 8 protons, which is a +8 charge. So for it to be neutral, it has to have a -8 charge from the electrons. That means -8 electrons. Okay? So for any neutral atom, the number of protons equals the number of electrons. Once we learn about ions, that'll change a little bit, but for now, they're going to be equal. Okay? And then the last column is the one that's a little bit difficult, but still really not that bad. It's the number of neutrons. And so for that, we need both of these. The mass number, remember, is the number of protons plus the number of neutrons. So if we take the mass number and we subtract the atomic number, we get the number of neutrons. Okay? If we take the mass number of phosphorus, 31 in this case, this is a particular isotope of phosphorus that has a mass number of 31. And if we subtract the number of protons in a nucleus of phosphorus, which is 15, we're going to get 16 neutrons. Okay? For zinc, in this case, the mass number is 65 for this particular isotope. And zinc always has 30 protons in its nucleus. So that means this particular isotope must have 35 neutrons. Here you see the answers. Let's do another example that might make it even clearer. So here we have 3 different isotopes of carbon. These are called carbon-12, carbon-13, and carbon-14. Okay? When you say the name of an isotope like that, you say the name of the element followed by the mass number. So carbon-12 really has a mass number of 12. Carbon-13 has a mass number of 13. Carbon-14 has a mass number of 14. Okay? You know these are the mass numbers because they're to the upper left of the symbol as written here. Okay? They're not in the lower left. So before we can figure out the number of protons, neutrons, and electrons, we have the mass numbers, but we need to know the atomic number, right? These symbols don't give the atomic number. Like I said, there's no number here. There's no lower number to the left of the atomic symbol. But again, that's fine because we know that we're dealing with carbon, and we can just look on the periodic table, and what we would find is that carbon is atomic number 6. So that means that every atom of carbon has 6 protons in its nucleus. So regardless of what isotope it is, it's going to have 6 protons. Okay? Since we're dealing with neutral atoms of carbon, then all of these atoms must also have 6 electrons. Okay? Then the only slightly difficult one is to figure out the number of neutrons, which is going to be, again, the mass number minus the atomic number. So for the first column, the mass number is 12. You subtract 6 protons and you get 6 neutrons. The second column, the mass number is 13, minus the 6 protons gives you 7 neutrons. And then for the last one, the atomic number is 14, so if you subtract the 6 protons from that, you get 8 neutrons. Okay? So again, they're all carbon, so they have all the same number of protons. They're all neutral, so they also all have the same number of electrons. But because they are different isotopes, they have different masses, and the different masses come from different numbers of neutrons. Now what happens if instead of having the isotope symbol in front of us, we're just told the particular subatomic particles that make up the atom that we're looking at? So in that case, we need to be able to recreate the atomic number and the mass number in order to write down the appropriate isotope symbol. So here's an example of that. Write the atomic symbol for atoms with the following subatomic particles. So the first one has 8 protons, 8 neutrons, and 8 electrons. B has 17 protons, 20 neutrons, and 17 electrons. And C has 47 protons, 60 neutrons, and 47 electrons. So the first thing that we're going to need is to figure out which element these each are, right? The element symbol or the isotope symbol has the element symbol. And so to do that, we need to figure out what the atomic number is. Remember, the atomic number is the number of protons. So A is atomic number 8, B is atomic number 17, and C is atomic number 47. Okay, this is very important. So what we should do is now consult the periodic table and look for those atomic numbers. Right, so here we have a periodic table, and atomic number 8 is over here in group 16, or 6A in the old system, and it's oxygen, atomic number 8. Atomic number 17 is in the halogens, group 17 or 7A, and atomic number 17 is chlorine here. And then last but not least, atomic number 47 is here. This is in the transition metal, so it's group 11 in the new system. Don't worry about the old system, but it is silver, Ag. Okay, that's atomic number 47. So now that we know that, we can go back and we can write the symbols, or we can start to write the symbols. Okay, so oxygen, chlorine, and silver. So we have oxygen, O, chlorine, Cl, and silver, Ag. Now we know the atomic numbers because that's what we're given in the number of protons. So we can just write the atomic number in the lower left, 8 for oxygen, 17 for chlorine, and 47 for silver. The only other thing we need in the isotope symbol, or the atomic symbol for the isotope, is the mass number. And remember, the mass number is going to be the number of protons plus the number of neutrons. So here we add these together and we get 16. So this is oxygen 16. Here we add them together and we get 37. So this is chlorine 37. And here we add them together and we get 107. And so this is silver 107. Now we've completed our isotope symbols. Notice we didn't really need to know the number of electrons. The number of electrons tells you whether you're dealing with a neutral atom or a charged ion of some sort, but it doesn't actually go into the atomic symbol. Now let's look at an example that doesn't tell us what element we're dealing with explicitly. It gives us the isotope symbol, which has the atomic number and the mass number, but instead of showing the actual element symbol, it just gives us an X as a placeholder. Right? There's no element X, so don't get confused. And it's asking two questions. The first is, which of the pairs below are isotopes of the same element? So of the 3 pairs listed, A, B, and C, which of those are depicting a pair of isotopes? And then question 2 is, of those 3 pairs again, in which of the pairs below do both atoms have 8 neutrons? Right? Now, the first question is relatively easy because we're talking about isotopes of the same element, and the thing that 2 isotopes will have in common is the atomic number, the number of protons. So we just look at the symbols and see which pair has the same atomic number for both, and that's the lower number. So in A, we have the first one with atomic number 8 and the second with atomic number 7, so it can't be A. In B, they do both have atomic number 6. So for B, they must be isotopes, right? C, again, we have different numbers, 7 and 8, and so it can't be C. So these are isotopes. Just to double check, we also want to make sure that they have different masses, right? One has a mass number of 12 and one has a mass number of 14. Then the second question is, which of the pairs both have 8 neutrons, right? Now this is a little bit more unusual, and in fact it doesn't give you the number of neutrons explicitly. The isotope symbol does not tell you explicitly how many neutrons, but it does tell you the mass number and the atomic number, and so by finding the difference you can calculate the number of neutrons. So you take 15 minus 8 and you get 7. You get 15 minus 7 and you get 8. So here, one of them has 8 neutrons, but the other one doesn't. So it is not A. For B, 12 minus 6 gives you 6 neutrons for the first, and 14 minus 6 gives you 8 neutrons for the second. So again, one of them has 8 neutrons, but the other does not, so it can't be B. And then for C, we have 15 minus 7, and that equals 8, and 16 minus 8, and that equals 8. So here, they both have the same number of neutrons. Same number of neutrons. And that's not particularly important because that doesn't tell you anything about the elements, right? They're not the same element. One is atomic number 7, one is atomic number 8. They don't even have the same mass. One has a mass number of 15 and one has a mass number of 16. So these are totally different elements in every way. It just so happens that they both have 8 neutrons, which doesn't really have any further significance. Here we see a table with the different naturally occurring isotopes of magnesium. Okay? We have magnesium 24, magnesium 25, and magnesium 26. Okay? Another way of writing these isotopes or specifying the isotopes is like this. We have the chemical symbol followed by a hyphen or a dash and the mass number. Okay? Sometimes you'll see the symbol or written out as the entire element name, magnesium 24. Okay? And so we see, since we're talking about magnesium, and magnesium is atomic number 12, all of these have 12 protons. When they're neutral, all of them also have 12 electrons. It shows us in the symbol the mass numbers, the number up top, 24, 25, and 26. That's where the mass number comes from. And then again, the number of neutrons is just the mass number minus the number of protons. So 24 minus 12 equals 12. 25 minus 12 equals 13, and 26 minus 12 equals 14. Okay, so that's how you get the number of neutrons again. And this table shows us something else. This table shows us two additional pieces of information. One is the actual mass of that particular isotope. Remember when we first learned about mass number, I said that the mass number is not actually the real mass of any particular atom. Okay, so, and I'm not even talking about the weighted average that the atomic mass on the periodic table is, right? This is the actual atomic mass for the magnesium 24 isotope here, right? But it's not exactly 24. If you remember, the proton and the neutron both weigh a little bit more than 1. So if you have 24 protons and neutrons together, and they each weigh a little bit more than 1, then how come the total mass is a little bit less than 1? Well, that's because of relativity and the conversion of matter to energy in the binding of the nucleus. Okay? That's not something you need to really worry about too much, but that is the explanation for why the actual mass of the isotope is always going to be a little bit less than the real mass number. Okay? The mass number is an integer because you're just counting protons and neutrons, whereas the mass of the isotope is something that's experimentally determined. Okay? It is always close though, so you can see 23.99 is close to 24, 24.99 is close to 25, and 25.98 is close to 26. Okay? And then the other piece of information that it gives you is the percent abundance. Okay? So this chart, we're assuming that these are the only 3 naturally occurring isotopes of magnesium. So that means that these 3 percentages have to add up to 100%. Okay? And they should within at least a rounding error. So that means that of all of the naturally occurring magnesium that you might find, 78.70% of it is going to be magnesium 24. 10.13% of it is going to be magnesium 25, and 11.17% is going to be magnesium 26. Okay? So unless you go through some sort of sorting process, some sort of actual experiment or laboratory procedure where you sort through elements based on the isotope mass, any sample of magnesium that you get is going to have this balance of isotopes. It's going to be 78.7% one, 10.13% of the other, and 11.17% of the third. Here you can see that shown as a pie chart, right? And also as a bar graph on the left. So on the bar graph here, you have most magnesium is magnesium 24, that's the largest part, and then roughly almost equal amounts of magnesium 25 and magnesium 26. Okay, just about 1% difference. And then in the pie chart, you can again see that this is the 78.7% piece of the pie, which is more than 3/4 of all magnesium atoms, right? So more than 3/4 of all magnesium atoms that you find are going to have a mass or be isotope magnesium 24. Okay? If you average these together, and not just averaging the mass by adding them and dividing by 3, but by actually taking the weight in terms of the percent abundance, then you get the atomic mass that's listed on the periodic table, which is 24.31 AMU. Okay? The reason that's listed on the table is because, again, any sample of magnesium that you get is going to be a distribution or statistical mixture of the different isotopes that on average will have this particular mass. So this is the useful mass that you're going to want to actually use in experiments and in calculating certain things that we'll see later. So how do we do this? How do we actually go through this process of calculating the atomic mass? Well, if you know what a weighted average is, then it's simple. You just take a weighted average. You take the mass of the individual isotopes and you weight it by the percent abundance. Okay? If you're not familiar with that, then we're going to go through it step by step here. Okay? So to calculate the atomic mass of an element, you need to know the mass, right? The actual mass of the isotope, not just the mass number, but the actual experimental mass, and the abundance for each isotope. And again, neither of these is something that you should really be able to predict in any sense. They're both just sort of empirical observations about the world. They're things that are measured and found out about the world. Okay? And so then once you have these two pieces of information, it's a relatively simple two-step process. For each isotope, you multiply the abundance by the mass of that particular isotope. Okay? Keep in mind that when we say multiply the abundance, right, the abundance that you're multiplying has to be a fractional abundance. So if you're given them in percentages, you have to take that as a fraction out of 100. Okay? And then once you have that for each isotope, you've multiplied the mass by the fractional abundance or the percentage abundance out of 100, then you just add together all of those components for each of the isotopes, for all of the isotopes. Okay? So let's see an example. Here we see the isotopes for chlorine. Okay? Chlorine consists of two naturally occurring isotopes, chlorine 35, and about 75.76% of all chlorine is chlorine 35, and that leaves about 24.24% of chlorine, which is chlorine 37. Okay? Again, in roundish numbers, it's about 3/4 chlorine 35 and 1/4 chlorine 37. So to actually calculate the atomic mass that you might see on the periodic table, again, you have to have the mass, the actual mass of the individual isotopes, not just the mass number, right? The mass number here is 35, but the actual mass is 34.97. Here, the mass number is 37, but the actual mass is 36.97. So you take this actual mass and you multiply it by the abundance expressed as a fraction. So chlorine 35 was 75.76% of all chlorine, and so you take 75.76 divided by 100, multiply it by 34.97. Okay? And then for the other isotope, you take its percent abundance out of 100, multiply it by the mass, and you get, well, 26.49 for the first, 8.962 AMU for the second, and then the last thing you have to do, step 2, is to add these two together. Okay? And so when you add these two together, you get 35.45 AMU. Okay? So keep in mind, this atomic mass that you're calculating, since it's going to be an average over a few different types of isotopes, it's usually going to be a decimal number. Okay? In some cases, it rounds so that it looks like a whole number, but it's never really a whole number precisely. It's a measured number. It's not an exact number. Okay? Also, keep in mind, there's no single atom with this mass. You're never going to find a single atom of chlorine that has a mass of 35.45. Okay? They all have a mass of either 34.97 or 36.97. But because most of them are 34.97, right, 3/4 of them are 34.97, this average is closer to that mass than it is to the other, right? The other is about 37 AMU. So 35.45 is closer to 35. Here we see a table that has some of these calculated weighted averages or atomic masses you might see in the periodic table. So for instance, lithium consists of two isotopes, either lithium-6 or lithium-7. But lithium-7 is by far the most abundant isotope. And you can tell because the average of the two is very, very close to the mass that you would expect for lithium-7, right? It doesn't tell us here what the exact mass of lithium-7 is, but we know that it should be very close to 7. And here, the average is also very close to 7. So it must be only a small percentage of lithium-6. Okay? So this last column tells us that the most abundant isotope is, again, lithium-7. For carbon, we have three isotopes, but the average is extremely close to carbon-12, and so that must be the most abundant isotope. Okay? Same thing with oxygen. In fact, for oxygen, we have what looks like a whole number, right? It's not really, and if you look in some periodic tables, it'll be 15.999 and some other numbers. But if we're rounding it to 2 decimals, then it's 16 for the weighted average, which is very, very close to oxygen 16, which is therefore the most abundant. For fluorine, there's only one stable isotope of fluorine, and it's fluorine 19, right? It has 9 protons and 10 neutrons for a total of 19 subatomic particles in its nucleus. That's its mass number. Here we see that its mass number is listed as 19.00. In reality, it's probably somewhat less than that, but it rounds up to 19.00, so we'll take that as the mass number. And you can go on and do this for the rest of them. Here's the example again with lithium, right? Lithium-6 and lithium-7 are the two possible isotopes. And this is saying use the periodic table to predict which isotope is the more prevalent one. So when it says that, what it means is look on the periodic table and find that the actual weighted average atomic mass is 6.941. Once you know that, then you can see that that actual weighted atomic average is much closer to 7 atomic mass units, which is what we would expect the mass of lithium-7 to be. That's close to the mass number of lithium-7. And so therefore, the most prevalent isotope must be lithium-7. And we can do another example using gallium. Gallium consists of 2 naturally occurring isotopes. So we have gallium-69 and gallium-71. Gallium-69 has a mass of 68.926 AMU, and gallium has an atomic mass of 70.925 AMU. And it also gives us the abundances. 60.10% is gallium-69, and 39.90% is gallium-71. So what is the atomic mass of gallium? Well, we have to go through this process again. And it helps to start by listing the different isotopes, right? So we have gallium-69 and gallium-71. And gallium-69 has an atomic mass, again, of 68.926 AMU. So we take the mass of gallium-69 and we multiply it by the fractional abundance, which is the percentage out of 100. And this equals 41.42 AMU. For gallium-71, we have an atomic mass of 70.925 AMU, and the fractional abundance is going to be 39.90 out of 100. Okay, always put your percentages out of 100. And this is going to be equal to 28.30 AMU. Okay, these have the number of significant figures that they have because of the abundances here. Okay, so there are 5 significant figures in each of the masses, but only 4 for each of the abundances. And so our answer is only going to have 4 significant figures for each component. And then when we add them together, Luckily, they both have the same number of decimal places, so we're just going to end up with 2 decimal places. And when we add them together, we get 69.72 AMU. Okay? And so if we look on the periodic table, we'll find that it says the atomic mass of gallium is 69.72.